इसको रिव्यू करते हैं। इसमें क्या क्या मेन चीज़ें हैं। सबसे पहले जो लोगों को इशू आता है वो आता है द कॉन्सेप्ट ऑफ डोमेन एंड रेंज। Domain, we all know these are the input values. Range, that is the output. Input means x values. Output means y values. The value of the function, fx values. अब किस किस टाइप के फंक्शंस हमारे पास है? We have linear function, that means a straight line. We have quadratic and we have reciprocal. These three would fall into the category of algebra. Naturally, there will be trigonometry also, and that's all about it. When we talk about a linear, let's go to each type one by one. If I talk about linear functions, that is the straightforward one. So linear functions, and for example, if I have a simple graph and the graph is something like fx equals to x plus 1, and we know that it's a straight line, compare it with y is equals to mx plus c. Gradient is 1, y-intercept is 1. Positive slope, y-intercept 1. So therefore, the graph would be something like this. Now, let me assign different domains to it. For example, domain, range. If the domain is x is an element of all real numbers, what does it mean? It means all real values of x. Real means values that you can see. Positive, negative, 0, decimal, fraction, integer. These are all real. Anything on the x-axis, anything on the y-axis. If the domain is all real values of x, the range is, in terms of fx, that's also all real values of x. Because you are going from here to here, y value should be going from here to here. Every single value is possible. Let me label the y-intercept as 1, and this time if I say the domain is x is greater than or equal to 0, and this is 0, and the corresponding y value is 1, and you are looking at the graph and you are seeing that if you go to the right of 0, the y value would be going up from 1. So therefore, the range fx is greater than or equal to 1. On the flip side, if I go to the left of 0, x is lesser than or equal to 0. So you would say that since you are going to the left, the y value is 1 and then down and then less. So therefore, fx is lesser than or equal to 1. Over here, we can think also in terms of proportionality. Directly proportional, x increases, y increases. Directly proportional, x decreases, y decreases. This is direct proportionality because the gradient is positive. Now let me limit this something like x lies between 0 and 2. So basically this is 0, somewhere here is 1, somewhere here is 2. The corresponding y value would be 3. The diagram is not drawn to scale, that's not an issue. If I am limiting myself between 0 and 2, so when I plug in 0 I get 1. When I plug in 2, I get 3. So f of 0 is 1. F of 2 is 3. Therefore, the range lies between 1 and 3. Since the domain is restricted between two values, the range is also restricted. Domain restricted, range restricted. Now, if I go to the idea of a quadratic graph. So now if I talk about a quadratic function, the most standard function is that of y is equals to x square or fx equals to x square. Let's first get started with this. Fx is equals to x square. The graph is something like this. Draw the graph like this, and let me just relocate it. It's passing through the origin. If the domain versus the range, the turning point is the origin in this scenario. If the domain is all real values of x, then look at the graph. That is the main thing. Look and then decide. The lowest y value is 0. All the other values are above it. So therefore, fx is greater than or equal to 0. Agreed? If I go to the right of turning point, x is greater than or equal to 0. You are going to the right. Y value is still rising up from 0. So therefore, fx is still greater than or equal to 0. Similarly, you are going to the left of 0. So now when you are going to the left of 0, the y value is still rising up from 0. So therefore, fx is greater than or equal to 0. Now look at these three. They all are exactly the same. The first, the second, the third. When you have drawn a graph with a minimum point, you can generalize it. When the graph is that of a minimum, either you take all real values domain or right of turning point or left of turning point, the range is the y coordinate of turning point and up and up and up. That is the scenario. Of course, drawing is a must. I'm just generalizing it. If I draw, on the other hand, the graph of y is equals to negative x square. So now the graph would be upside down, something like this. And again, domain and range. Fx is equals to negative x square. The above one was positive x square, this is negative x square. And let me have three possible domains for this. The first one, x is an element of real number. Over here, the turning point is still 0, 0. To the right of turning point, to the left of turning point. All these three will give me the same exact answer, the same exact range. What is the range? The range is fx is lesser than or equal to 0. Because when you have a maximum point, the range would be lesser because that's the maximum that you have reached. How can you even go up? So fx is lesser than or equal to 0. Fx is lesser than or equal to 0. So you can generalize that whenever it's a graph of a maximum, whether you go right of turning point, whether you go left of turning point, whether you take all real values domain, the range would be lesser than or equal to the y value. And you will see this more in the upcoming examples. So these two are the first two basic examples of quadratics. Let me move on. Something like a graph of fx equals to x minus 1 whole square plus 4. Underneath it, write ax minus h whole square plus k. A is positive, that is the shape of the graph. H equals to 1, k equals to 4. 1 comma 4 is the coordinate of the turning point. And first of all, I'll draw separate graphs in this scenario. 3 or 4 maybe separate graphs. So let me first copy this. One more can fit in. Okay. Now the first one is domain. X is an element of real numbers. Range, I'll draw and write. So first of all, the graph is something like this. This is 1 and this is 4. That's the coordinate of the turning point. It's a graph of a minimum and 1 comma 4 is the turning point. Now when we have all real values, look at the graph. Y could assume, Y is the same thing as function, Y could assume all values which are greater than or equal to 4. That's the least. That's why it's called a minimum. So this is the minimum. This is the least Y value. So all other values would be greater than or equal to this. Therefore, fx is greater than or equal to 4. Correct? Same graph, domain, x is greater than or equal to 1. And one more domain, x is lesser than or equal to 1. So you won't draw the full graph, you would draw half graph. How would you draw half graph? You would draw to the right of 1 comma 4, something like this. And over here, you would draw something like this. Both the turning points are 1 comma 4. So this is 1 comma 4. This is 1. And this is 4. This is 1 and this is 4. Now look at the graph. The purple graph going to the right. So fx is greater than or equal to 4. Again on the other side, range, fx is greater than or equal to 4. That means I can say over here, if I shift it a bit, and if I write for this purple one, whenever it's a graph of a minimum and for 3 domains, all real values, right or left of turning point, these are the 3 possible domains. The range would be fx is greater than or equal to the y coordinate of turning point. Agreed? Have a look over here. All real values and right of turning point and left of turning point. The range is all the same, that is to the above the turning point, y coordinate of turning point. That means now I can generalize and then I'll draw the diagrams. What would be the generalization for the next one? If it's a graph of a maximum and you have the domain all real values of x, you have the domain right or left of turning point, then your range is fx is lesser than or equal to y coordinate of turning point. So this is your domains and this is your range. Now let me not use this thing over here, and over here let me draw a graph of a maximum. 3 sketches for this. For example, if I have fx equals to minus 2 x plus 1 whole square plus 3. This is a x minus h whole square plus k. A is negative, therefore it's a maximum. Minus h is plus 1, therefore h is negative 1, therefore k is plus 3, therefore minus 1 comma 3 is the coordinate of the maximum point. Just like this turning point was actually a minimum. Yes, it's a turning point, but it's a minimum. It's a maximum type of turning point. So now minus 1 comma 3, that 2 will do nothing. That 2 is just for steepness. So let me draw the graph. First of all, minus 1, 3 is somewhere here. So something like this. And then something like this. And then something like this. I'm drawing 3 graphs. The first graph, the domain is x is an element of real number. This is minus 1 and this is 3. And fx is lesser than or equal to 3. Over here, this is 3. This is negative 1. Similarly, this is more or less the same. Let me just pull it down. This is negative 1. This is 3. In the second one, domain, x is right of turning point. Range, fx is lesser than or equal to 3. Domain, x is left of turning point. Range, fx is lesser than or equal to 3. So it exactly tallies with the orange statement. Now let me restrict the domain. That is the next step. So now we are still on quadratics. And if I talk about a restricted domain, that means it's between 2 values. That is what it means. Let me take the very first graph. Fx is equals to x minus 1 whole square plus 4. A x minus h whole square plus k. A is positive. That's the shape. Minus 1 comma 4 is the coordinate of the turning point. And this turning point is in fact a minimum. Now let me first evaluate some numbers. For example, if I plug in 0, I get 5. If I plug in 2, I'll still get a 5. If I plug in 3, I'll get an 8. And one more thing, if I plug in minus 1, that is again an 8. Now this is also a mystery, actually not a mystery as such. Okay, why 2 values are giving me the same answer? So let me focus on the symmetry part also. If I draw a number line and this is the x coordinate of turning point, which in this scenario is 1. And over here I have the x value, which is 0. I have the x value, which is 2. So 0 is 1 unit lesser than x coordinate of turning point. 2 is 1 unit greater. So that is why both y values are coming out to be the same. Got the idea? The curvature is the same. You have the turning point, that is the symmetry, that's the center point, let's call it. So one x coordinate ahead, you get the same y value. One x coordinate below, you get the same y value. Similarly, why is 3 giving me the same answer? Why is minus 1 giving me the same answer? Because 3 is 2 units ahead of 1. And minus 1 is 2 units below, lesser than the x coordinate of turning point. That is the logic behind it. That is the symmetry behind it. Now, if I draw that thing, a graph, and this time, if I restrict it between domain, x lies between 1 and 3. So we know that 1 is the x coordinate of turning point. So therefore, f of 1, we already know it's 4. F of 3 is written on the side, we already know it's 8. So therefore, the graph is something like this. It's just a small portion. It's not drawn to scale. So this is 1 versus, let me reduce this a bit. And this is 3. So 1 is giving me 4 and 3 is giving me 8. So now focus on the y-axis. When you focus on the y-axis, you are looking at 8, you are looking at 4. So therefore, your range fx lies between 4 and 8. Makes sense? But if I have the same graph and now I have fx, the domain, the fx is still the same, the domain, x lies between 0 and 3. So we know that f of 0 is 5, f of 3 is 8. F of 0 is 5, f of 3 is 8. Now first thing, when you have 0, you have 5, something like this. So this is 1 point. When you have 1, you have 2, you have 3, you have 3, you have 8. This is the other point. Is the graph going like this? No, the graph is not going like this. How is the graph going? The graph is passing through the turning point. So since the graph is passing through the turning point, so this is 1, this is 4, so therefore take care of it. The x coordinate of turning point is part and parcel of this domain, so you have to take care of it. The first one, it was part of it, but not in the middle. Got the idea? Got the difference? Think again. Yes, the turning point was there, but that was the initial point. It was not in between. Over here, x coordinate of turning point lies in between the domain. So that changes the whole scenario. You have to plug in 0, you have to plug in 3. 0 is giving me 5, 3 is giving me 8. What is the x coordinate of turning point giving me? So the x coordinate of turning point 1 is giving me 4. Now look at the y-axis. What do you see? You see 8, you see 5, you see 4. Which is the lowest value? 4. And which is the highest value? 8. So therefore, the fx lies between 4 and 8. Got the idea? Now the same rule applies even if I change the function. Let me choose a function. Fx equals to minus x plus 2 whole square. Yeah, let me change this to minus x minus 2 whole square plus 5. This is a, x minus h whole square plus k. A is negative, that's the shape. H is 2, k is 5. 2 comma 5 is the coordinate of the turning point, which is in fact a maximum, right? So now if it's a maximum, let's draw the graph, but after the range. And this time I'm not calculating the value from before, I'll calculate it later. If my domain is x lies between 1 and 3, and let me draw another one. Another domain is x lies between, x coordinate is 2, so therefore if I take 0 and minus 3. Now in the first one, when I do the calculation, f of 1 minus 2 is negative 1, negative 1 square is 1, there is a minus before, so minus 1 plus 5 comes out to be 4. Let me plug in 3, 3 minus 2 is 1, actually it's the same thing, so let me change the number, because it won't give the same answer, because two values would be the same. This is 4, this is 4. 4 minus 2 is 2, 2 square is 4, minus 4 plus 5 is plus 1. Now f of 1 is 4, so over here, somewhere here is 1, and it's giving me 4. And f of 4 is 1, so this is 2, and this is 3, and this is 4. F of 2 is giving me 1. And what is the x coordinate of turning point part of the domain? What is the x coordinate of turning point? 2. Is it part? Is it in between? Yes. So x coordinate of turning point is in between the domain. So therefore take care of it. F of 2 is giving me 5. It's already written over there. Therefore 2 is giving me 5. So 2 is giving me 5. Something like this. Now what are the y values that you see? You see 1, you see 5, you see 4. As such, you don't even need to draw the graph. The graph is just for guidance. Basically, I am deciding on the 3 y values. So if the 3 y values, if I can write it on the side, what's the need of the graph? Unless the examiner asks for it. So what is the smallest y value? The smallest y value is 1. What is the highest y value? 5. So fx lies between 1 and 5. Coming back over here, f of 0 and f of minus 3. So 0 if I plug in, minus 4 plus 5 is 1. Minus 3 minus 2 is minus 5. The number would be too large to draw. So let me just change the number. So instead of minus 3, let me plug in minus 1. Minus 1 minus 2 is minus 3. Minus 3 square is plus 9. There is a minus before. Minus 9 plus 5 is minus 4. Second thing, what do I need to check? Is the x coordinate of turning point somewhere in between? No, it's not there. X coordinate of turning point is not part of domain. So do not take care of it. So I don't even need to write it. Actually, my answer is right around the corner. I don't even need to draw it. So this time I'll first write the answer. Fx lies between minus 4 is the lowest value, 1 is the highest value. And if you want to draw it, you can just for reference, just to get the diagram straight, this is 2 is giving me 5, but it's not part of the graph. And 0 is giving me 1. So 0 is giving me 1, that is something like this. And minus 1 is giving me minus 4. Minus 1 is giving me minus 4, something like this. So basically, this is the portion of the graph that is drawn. Something like this. Actually, the whole graph would have been like this. But we are not interested in the whole graph, we are just interested in this part. So therefore, the range lies between such and such. Now, that was all about quadratics. Now, let me move to the reciprocal graphs. So, if I talk about reciprocal functions, there are two types actually of reciprocals. The first type is, let me draw it side by side. So, out of these two types, what is the difference between the two? The first graph is of the form fx equals to a constant, a positive constant divided by x. The other one is fx is any positive constant divided by x square. The first graph looks like this. The first quadrant and the third quadrant. Something like this. The second graph is something like this. Why? Because if x is positive, fx is positive. That is the first quadrant. If x is negative, y, fx is also negative. So first quadrant, third quadrant. Let me label it. So this is in the first quadrant, this is in the third quadrant. That is the first and foremost thing. Fx is equals to k over x square. If x is positive, x square is positive. Therefore, y is positive. So again, it belongs in the first quadrant. But even if x is negative, x square would be positive. Therefore, y would be positive. So x is negative, x square is positive, therefore y is positive, therefore the second quadrant. So remember this rule. First, third, first, second. Now, if I talk about the domain for this particular graph, for the first one, x is all real values of x except x cannot be 0. Because if x is 0, the function becomes undefined. Any number divided by 0, the function is undefined. Therefore, the range in this scenario is y or fx is also element of real number, but fx cannot be 0. The x coordinate is not 0, the y coordinate is not 0. For the second one, what is my domain? The same as the first one. So domain is x is an element of real number. At the same time, x should not equal to 0. But now what is the range? It's not all real values. It's only positive values. So therefore, if x is greater than 0, not equal to, greater than 0, I think that says it all. Because I don't have to write x not y not equal to 0, because it already says if x is greater than 0. Got it? Now what if I apply a negative sign to each one of them, and that is in transformation of functions. So if I apply a negative sign, the purple one, let me denote it by red. So the first quadrant becomes the fourth and the third becomes the second. This is the graph of fx equals to negative k over x squared. So because of this negative sign, it gets flipped in the x-axis. My bad. Bilkul sahi. So therefore, this is fx is k over x. Perfectly right. The first quadrant gets flipped into fourth and the third gets flipped into second. So this is fourth and this is second. Similarly, the green one, if I draw it with some other color, orange, so therefore now it would be like this. Let me just first draw this thing a little bit up. Something like this. Something like this. So therefore, fx is equal to fx equals to negative and then k over x square. So because of this negative sign, it gets flipped. The first goes to fourth, second goes to third. First goes to third and second, this is fourth and this is third. So this is the basic idea about this. One more idea. That is, it gets very close to the x-axis but does not actually touch it. It gets very close to the x-axis, does not touch it, and so on. That is why those values are not there. So this is the vertical and the horizontal asymptote. X-axis is y is equals to 0, y-axis is x is equals to 0. Y equals to 0, x is equals to 0. The same goes over here, because now when we'll do the transformation, we're also going to take care of it. This is y is 0, this is y is 0, this is x is 0, this is x is 0. Now, if we apply transformation to this, transformation of reciprocal functions. So, I can give you a standard form which is convenient to many. That is, let me write it as two separate ones. Y equals to a x minus h raised to power of 1 plus k versus y is equals to a over x minus h raised to power of 2 plus k. When I have taught you in the original class, I have written n could be 1, n could be 2. This time I have separated it out. This thing is like y is equals to k over x, because the power is 1. And this one, the other one, this is similar to, let me create more space. This is similar to y is equals to k over x squared. Correct? Because of this power of 2. What is A? A just tells you the steepness. If A is positive, it's in the, for example, in this one, you don't have to actually remember it. Again, you have to remember it, not actually write it down, first and third quadrant. So in this scenario, if A is positive, this is first and third. Naturally, if A is negative, that would be fourth and second. So let me write this thing as second and fourth. This is second and fourth. Over here, If A is positive, that is first and second. And over here, if A is negative, that is third and fourth. If you remember the original one, you know how to flip it. What is H and K? It looks very similar to completed square. It's in that format. But X is equals to H is the vertical asymptote. And Y equals to K. In both the scenarios, that is the horizontal asymptote. I'll draw and then you will understand. For example, if I want to draw Y equals to or Fx equals to, have I written Y? So let's go with Y. 1 over x minus 2 plus 3 versus y is equals to 1 over x minus 2 whole square plus 3. The first one is something similar to the original one, like this, because the value of A is positive, and the second one is similar to this. So that's the first thing. It's only shifted to the sides. So therefore, in this scenario, 1 over x minus 2, first of all, focus on this one, focus on this 2. X minus 2 is like x minus h. So x is equals to h, x is equals to 2, that is the vertical asymptote. So x is equals to 2 is the vertical asymptote. The same goes on the other side. X is equals to 2 is the vertical asymptote. That is for this, that is for this. And y is equals to 3, that is the horizontal asymptote. Y is equals to 3 is the horizontal asymptote. Make sense? This is x equals to 2, y equals to 3. X equals to 2, y equals to 3. Now these are your new x-axis and y-axis. This is after the transformation. So now when you draw the graph, you would draw it like this, something like this. You can always extend the axes, and it's like this. And over here, how would you draw? You would draw it like this, and you would draw it like this. So what is the range of the first one? First of all, what is the domain of the first one? The domain of the first one is x is an element of real numbers, but x does not equal to 2. What is the range? If x is an element of real numbers, but fx does not equal to 3. On the right side, domain, x is an element of real number, x does not equal to 2. What is the range? Greater than 3. If x is greater than 3. It does not include 3. Now, for example, if I had a 5 over here, it wouldn't change anything. If I have a 7,000 over here, it won't change anything, because it's the steepness. If I have a minus 1 over here, yes, it will be flipped. It would be like this, it would be like this. If I have a minus over here, it would be like this, it would be like this. Basically, instead of teaching you transformation over here, I have taught you according to this formula, which used to be part of SAT 2 Math 2C test. If I can also teach it to you according to the transformation. For example, if I have, without any formula, y is equals to 2 over x. Yeah, let me first draw the original one. 1 over x minus 2 plus 3. And the examiner would say, the original function, let me denote it by gx, and fx is 1 over x. And let me make this thing into a proper exam type question about steps of transformation. And the examiner would say, write down 2 transformation that will change fx into gx. Now think. First focus on the x, this becomes -2. Then focus on this thing, which is this +3. That means, what have you done? Fx is changed into something else. Let me call this thing as hx. Then hx is changed into gx. First of all, what you have done is that you have shifted the graph sketch 2 units to the right, because minus sign with the x has 2 units to the right. Exactly, that's what you have done. So even if you don't have any knowledge of that formula, you can also do it by transformation. And what is the next step? The next step is then the hx is then translated or shifted, doesn't make a difference. Translated 3 units up. That's how the graph is drawn. Let me make more question on this. Let me draw a line first. And now if I have fx equals to 1 over x squared and gx equals to -1 x plus 3 whole square plus 4. The examiner would ask, write down 3 transformation that maps fx onto gx. What are those 3 transformations? First of all, I can flip it later, I can flip it in the beginning. So let me first flip it. So I have fx and hx and wx and gx. So 4 functions, because there are 3 transformations. The first transformation is like this. The second one is this green one, and the last one is the purple one. In the first one, flip sketch in x-axis. That is because of this negative sign. What is the next step? Next step is move horizontally, shift, then shift the graph horizontally by 3 units to the left, because now it's a plus sign. So since it's a positive sign, you are shifting it to the left. And last but not the least, what does it say? Then translate the graph up by 4 units. So usually the examiner asks for 2 transformation. I have done 3. So this is the +4, and that's how this thing is done. So I think that is a quick review about functions. Of course, something about the composite and more exam type question. There will be a lecture that I'll upload, and anything else, let me know so I can make a lecture on that. Take care.